Pause this video right now and answer this. A factory machine runs for 1,600 hours and breaks down 4 times. Repairs take 200 hours total. What percentage of time is this machine actually working? Don't worry if you're not sure. In the next few minutes, you'll not only solve this problem, but you'll master availability calculations for any system. Let's get started. Welcome to Academic Engineering, where we break down complex engineering concepts into simple, step-by-step solutions. Today, we're starting a brand new series on quality and reliability engineering, and we're beginning with one of the most important metrics in any industry, system availability. Whether it's manufacturing, IT infrastructure, healthcare, or aviation, understanding availability can literally save millions of dollars and even lives. By the end of this video, you'll master what availability actually means, how to calculate MTBF and MTTR, single machine availability, series system calculations, and parallel system configurations. Let's dive into concept number 1. Let's start with the fundamentals. Availability is simply the proportion of time a system is functioning correctly. Imagine a conveyor belt in a factory. It's supposed to run 24/7, but sometimes it breaks down and needs repairs. Availability tells us what percentage of time is it actually running. Mathematically, it's simple. Uptime divided by total time. Or more precisely, uptime divided by uptime plus downtime. Here's a quick example. A machine runs for 90 hours, then breaks down for 10 hours. Total time is 100 hours. Availability equals 90 divided by open parentheses, 90 plus 10 close parentheses. Availability equals 90 divided by 100. Availability equals 0.90 or 90%. So this machine has 90% availability. Easy, right? But here's why this matters. In automotive manufacturing, 1 hour of downtime can cost $50,000 to $100,000. In a power plant, it could mean blackouts affecting thousands of homes. In a hospital, it could impact patient care. So calculating and improving availability isn't just math, it's critical business strategy. Now, to calculate availability in real scenarios, we need 2 critical terms, MTBF and MTTR. Let's break them down. MTBF stands for mean time between failures. This is the average operating time before a machine fails. Let's say a machine runs for 400 hours, fails, gets repaired, runs for 500 hours, fails again, then runs for 450 hours. The MTBF is the average of these operating periods. MTBF equals open parentheses 400 plus 500 plus 450 close parentheses divided by 3 equals 450 hours. P insight. Higher MTBF means more reliable. A machine with an MTBF of 1,000 hours is more reliable than one with 200 hours. MTTR stands for mean time to repair. This is the average time needed to fix a machine after it fails. If a machine breaks down 3 times and repairs take 2 hours, 3 hours, and 1 hour respectively, MTTR equals open parentheses 2 plus 3 plus 1 close parentheses divided by 3 equals 2 hours. Key insight. Lower MTTR means faster recovery. We want repairs to be quick. Here's the golden formula. Availability equals MTBF divided by open parentheses MTBF plus MTTR close parentheses. Notice, if we increase MTBF, make the machine more reliable, availability goes up. If we decrease MTTR, fix it faster, availability also goes up. This formula captures both factors. And that's the fundamental goal in reliability engineering. Now, let's apply this to real problems. Let's solve the problem from the beginning of this video. Here's what we know. Given operating time equals 1,600 hours, number of failures equals 4 failures, total repair time equals 200 hours. Find machine availability. We'll solve this in 3 clear steps. Step 1. Calculate MTBF. Formula: MTBF equals operating time divided by number of failures. We take the operating time, which is 1,600 hours, and divide it by the number of failures, which is 4. MTBF equals 1,600 hours divided by 4. MTBF equals 400 hours. So our MTBF is 400 hours. This means on average the machine runs for 400 hours before experiencing a failure. Step 2. Calculate MTTR. Formula: MTTR equals total repair time divided by number of failures. We're given that total repair time is 200 hours and we had 4 failures. MTTR equals 200 hours divided by 4 failures. MTTR equals 50 hours. So MTTR is 50 hours. Each time the machine fails, it takes on average 50 hours to repair. Let's summarize what we have so far. MTBF equals 400 hours, MTTR equals 50 hours. Step 3. Calculate availability using our golden formula. Formula: A equals MTBF divided by open parentheses, MTBF plus MTTR close parentheses. We plug in our values. MTBF is 400, MTTR is 50. A equals 400 divided by open parentheses, 400 plus 50 close parentheses. First, we add the denominator. 400 plus 50 equals 450. Now we divide. 400 divided by 450 equals 0.889. And converting to percentage, 0.889 equals 88.9%. There's our answer. The machine has 88.9% availability. So what does 88.9% actually mean in practice? The machine is operational 88.9% of the time. Out of 100 hours, the machine is down approximately 11 hours. For a 24/7 operation, that's 8,760 hours per year, which means downtime of approximately 972 hours per year. That's over 40 days. Is that acceptable? It depends on your industry. But here's the power of this formula. Watch what happens when we improve our metrics. If we reduce repair time to 25 hours, maybe by training technicians better, availability jumps to 94.1%. Or if we improve reliability and double MTBF to 800 hours through better maintenance or better components, we also reach 94.1%. See how powerful these levers are? That's why engineers obsess over MTBF and MTTR. Great, you've mastered single machines. Now let's level up to system configurations. First up, series systems. In a series system, components are arranged one after another. The key rule is all components must work for the system to function. Think of it like a chain. If any link breaks, the entire chain fails. Same here. If machine A fails, the whole system stops, even if machine B is working perfectly fine. Let's solve a problem that shows how powerful this configuration is. Problem 2. Series system availability. Given, machine A has availability of 95% or 0.95, machine B has 90% or 0.90, configuration, series, find total system availability. For series systems, here's the formula you must remember. A total equals A1 times A2 times A3 and so on. In other words, multiply all individual availabilities. Why do we multiply? Because we need both to work simultaneously. The probability of both working is the product of their individual probabilities. Let's calculate. A total equals A sub A times A sub B. A total equals 0.95 times 0.90. 0.95 times 0.90 equals 0.855 or 85.5%. Now, here's a critical insight that many students miss. Machine A alone has 95% availability. Machine B alone has 90% availability, but the system in series has 85.5% availability, lower than both. The system availability is always lower than the worst component. In fact, it's lower than both components. This is the harsh reality of series systems. Let's take this further. What if we add a third machine with 88% availability? A total equals 0.95 times 0.90 times 0.88 equals 0.7524 or 75.24%. See what happened? We dropped from 85.5% to 75.24%. The more components you add in series, the worse your availability gets. So how do we fix this? That's where parallel systems come in, and they're absolutely brilliant. Let's explore them next. Now, let's talk about the game changer, parallel systems, also called redundant systems. In a parallel configuration, the system works as long as at least one component is functioning. This is how engineers build reliability into critical systems. Think of it like having a backup. If machine A fails, machine B keeps the system running. Both would have to fail simultaneously for the system to go down. Let's solve a problem that shows just how powerful this configuration is. Problem 3. Parallel system availability. Given, machine A has availability of 90% or 0.90, machine B has 90% or 0.90, configuration parallel. Find total system availability. Here's where it gets interesting. For parallel systems, we can't just multiply availabilities. We need a different approach. Step 1. Calculate unavailability of each component. U equals 1 minus A. Step 2, multiply unavailabilities. U total equals U1 times U2. Step 3, convert back to availability. A equals 1 minus U total. Let me explain the logic. Unavailability is the probability that a component is not working. For the system to fail, all components must be down simultaneously. Step 1, calculate the unavailability of each machine. U sub A equals 1 minus A sub A equals 1 minus 0.90 equals 0.10. U sub B equals 1 minus A sub B equals 1 minus 0.90 equals 0.10. So each machine has a 10% chance of being down at any given time. Step 2. Calculate total unavailability, the probability that both fail together. U total equals U sub A times U sub B. U total equals 0.10 times 0.10. U total equals 0.01. Only a 1% chance both machines are down simultaneously. That's the power of redundancy. Step 3. Convert back to availability. A total equals 1 minus U total. A total equals 1 minus 0.01. A total equals 0.99 or 99%. 99% availability. That's phenomenal. Look at this comparison. A single machine gives us 90%. Two machines in series drops us to 81%, but two machines in parallel shoots us up to 99%. Want to see something even more impressive? Let's add a third parallel machine. With three machines in parallel, each at 90%, we get 99.9% availability. This is why critical systems like aircraft controls, hospital life support, and data centers use parallel redundancy. It's not about cost, it's about reliability and safety. Of course, there's a trade-off. More components mean higher cost and complexity, but for critical applications, the improved reliability is absolutely worth it. Before we wrap up, let me share 4 critical tips to help you avoid the most common mistakes students make. Tip 1. Don't confuse MTBF and MTTF. MTBF is for repairable systems, things you can fix. MTTF is for components that fail once and you replace them, like light bulbs or fuses. Tip 2. Never forget, series systems always reduce availability. If someone tells you adding a component in series improved reliability, they made a calculation error. Tip 3. Unit consistency is critical. If MTBF is in hours and MTTR is in days, convert them to the same unit before you calculate. This is an extremely common error. Tip 4. Availability is a probability, so it must be between 0 and 1, or 0% to 100%. If you get an answer greater than 1 or negative, you've made a mistake. Go back and check your calculations. Bonus tip. Always do a sanity check. If your machine spends more time broken than working, availability should be less than 50%. Use logic to verify your math. Alright, let's do a lightning-fast recap of everything we covered today. We learned availability definition, MTBF and MTTR concepts, single machine calculations, series system availability, which always decreases, and parallel system availability, which dramatically improves reliability. In our next video, we're diving deep into MTBF calculation methods, including Weibull distribution, failure rate analysis, and how to predict component lifetimes. You'll definitely want to catch that one. If this video helped you understand availability calculations, smash that like button. It helps us reach more engineering students. And subscribe to Academic Engineering so you never miss an episode in this quality and reliability series. Drop a comment below and let me know which concept clicked for you, and what should we cover next in this series. Your feedback shapes our content. Check out our other engineering series, Project Management, Heat Transfer, and Engineering Mechanics, all linked in the description and on your screen now. Remember, engineering success isn't about memorizing formulas. It's about truly understanding the concepts and applying them confidently. You've got this. Thanks for watching Academic Engineering. I'll see you in the next video.